Well, hello and greetings from Northern Michigan. This is Bob the Science Guy. This is part 2 of our study of perspective using my shiny new whiteboard. Now, as you recall from part 1, we would draw a line that represented the ground. Then we would draw a line parallel to it that would represent the sky. Our eye would be halfway between. Now, this is our eye level right here. Now, if we draw some stars up in the sky, we can clearly see that what we need to do is we need to look up at a certain angle to see each of those stars. And as the stars go further away from us, that angle decreases. Now, as we get out towards infinity, that angle will end up right on the horizon. Likewise, if we look at some beach balls on the ground below our eye level, we have the same process, and as this goes off to infinity, this all settles down right at our eye level, causing a horizon. Let's take a moment in this video and see how that works out in the real world on the real horizon. So let's cue up the music and get started. Okay, now when we get started, the first thing I want to do is I want to talk about the Rayleigh Criterion again. This is the formula where we determine how far apart things can be in order to be distinctly recognized as two separate objects. And it has to do with a critical angle. Now the formula was 1.22 times the wavelength of light over the diameter of the aperture, such as your pupil or an f-stop on your lens, whatever the case may be. Now, we talked a little bit about this wavelength. The wavelength of light that we can see is somewhere between 380 and about 720 nanometers, which is 1 times 10 to the negative 9th meters. We used an example of 500. But looking at this formula, if we make the wavelength of light smaller, such as 380 nanometers, the resultant answer will be a little bit smaller than the 500 that we used. Now, if we use 720, it'll be a little bit larger. So, if the radian or the critical angle is larger, such as with 720 nanometers, we will not be able to tell them apart at a closer distance than if the wavelength of light was smaller. Now here's what I'm talking about with that. We used 500 nanometers, and we said that we could see a 12-foot object at about 18 miles. If we used 380 nanometers, this critical angle would end up being smaller, and as a result, we could see that 12-foot object at greater than 18 miles. Likewise, if we used 720, we would see it at less than 18 miles. Now, the true horizon on Earth says that we see that object at 8 miles, and then it disappears completely. Now, for example, on this photograph, these are two freighters out on the Great Lakes. You'll see the red freighter in front, and then you'll see a white freighter in the back. But notice how very sharp that horizontal horizon line is. There's no blurriness whatsoever, and you can clearly see the difference between the sky and the lake water. Okay, let's have a look and talk about what happens when objects are on the ground or in the air above the observer. I'm going to draw this from the side on the left. That's not working out. So what I'm going to do is I'm going to draw this from the side on the left and from the front on the right. So on the side, we're going to have green water and blue sky. And then we're going to have an observer right in the middle. In the sky, we have stars. And on the water, we're going to have beach balls. Now, these beach balls will never be in the sky, and the stars will never be under the water. That should be quite clear. Now, if we look at the angle that is formed as the eye looks at the beach ball and the star, it's actually quite wide at first. As the objects become more distant, that angle decreases. And then eventually, what will happen is it will approach 0. Now, if you look at this going out towards the horizon, you're going to see this angle represented by a flat horizon in front of you. Now, the stars, which start off here and work their way out, will start off looking like this. Like that. Now the beach balls will likewise start off here and then work their way up towards the center where the horizon is. Now to sum this up, if you have a horizon that is directly at your eye level, everything that is below your eye level will come up to that horizon. Everything that is above your eye level will come down to the horizon, like so. It would all disappear in a vanishing point right here. There is no way that something that is above the horizon here could ever drop below it. Likewise, there's nothing that is below the horizon that could ever come above it. Now this is actually an interesting photograph of the wing of my airplane. I'm in level flight, and as you can see, I'm flying above the clouds. My seat in the aircraft is above this wingtip. If you were to draw a line from wingtip to wingtip, straight across, my head would be above it. If the horizon was level with my eye level, I would look straight out and the horizon would be above the wingtip. But instead, the horizon is actually below the wingtip in that direction. And there's the angle that goes down to the horizon. Now let's go ahead and have a look at a mountain. And it's over the ground. Now our eye is right here on the mountain. This would be our level line of sight from eye level. The distance here would be the same as the distance here. Now, if we were to look down at objects on the ground, we would form an angle from our level of that. As the objects became further away, that angle would decrease and the objects would appear to rise up towards our eye level. Now, the easiest way to look at that is here's our eye level. Here's the first object here. Here's the second object at a slightly different angle, little smaller angle. And the third object right there would be coming up. As the angle decreased, the object moved towards our eye level. The same could be said of objects coming down from the sky. Now, if indeed the Earth was curved, like so, and we were on a mountain here, and this would be our eye level, this would be level, and this would be the angle drop to our horizon. So, if we were actually looking at the horizon, we would be looking down. Now, once again, if we have objects along here, we would be looking down to them. However, if we had an object over here, we would be blocked by that part of the Earth and we wouldn't see it at all. So what we would see is this one would be down here. This one would be coming up. This one would be almost there. That one would be just above it. And this one down here wouldn't be seen at all. And if we looked at a level, this level, that would be up here. So let's see if that's what actually. Now, if you look at this example of a water level, you can very clearly see that the eye level is determined by these two levels of this water level. The horizon is actually dipping below that. Now, on a flat Earth, on a flat plane, due to perspective, the horizon would be at the same level as these two red water levels. But on the Earth, in the real world, the horizon is in fact below the eye level of the observer. Now, on the Earth, if you were to look at a water level like we just did, we could determine what the level of our eye level was based on looking at how high the fluid was in the water level. Now, underneath it, we will see where the land is. And above it, in this area, would be sky. Up here would be sky. This drop right here can be measured. It's generally listed as a number of degrees. Now, based on how many degrees that drops, we can actually determine how much of a curve there is. And again, after we have determined the curve, we can actually determine what the radius of that curve is. Now that gives us a couple of very interesting things that we can do. Since if we are located on the Earth and we can determine how much of a curve is this way and determine how much the curve is that way, we can also determine how much the curve is this way and that way. Because it will be the same horizontal drop in all directions from any spot on Earth. Now that tells us two different things. Not only can we do this for one spot, we can also do it for a spot over here. And what we end up finding is that we have a spherical object such as that has a center and has a radius. And that radius is determined by direct measurement of this horizontal drop. And the other thing that we can measure it by is if we had a building out here, we could determine how much of that building was hidden and how much was visible. That information also confirms what a radius is. And if both measurements of the radius agree with each other, that is very strong evidence that that is the correct radius. So let's just finish up with a couple of things. If there is a curve, that curve will have a radius. Now, if the surface of the Earth is curved, and we are on a mountain, and we look straight out in both ways, this red line will be level. It will also be at a right angle to this radius line or plumb line going straight down. If there is a drop from our point of view to the horizon of a set angle, we can use that to determine the radius of this curve. Okay? Next, if we have a building out here that is a certain height, and we can see this much of the building, but we can't see that much of the building. That can be measured. That can be used to specifically calculate a radius. Next, if the sun is straight up that way, we can measure an angle of a shadow elsewhere on the Earth to determine where this spot is in relationship to that spot by degrees. So right there is 3 direct measurements of the radius of the Earth. This latter one here finds the radius by calculating the circumference. You know, there's one last thing that I would like to cover. Recall this diagram. Now, we talked about a building that was a certain elevation, 12 feet, for example. What would happen if we put that building out at a 45-degree angle? We could still have 12 feet here, but it would only be the same size as a 6-foot building. You see how that would be? Because it's at an angle, even though it starts at the same spot, it doesn't go to the full height as the building that is straight up because it's at a 45-degree angle. And that brings it down to half height. So, if the angle between the top and the bottom of the building is the critical factor in whether or not we could see a difference between the top and the bottom of a building, if we tilt this at 45 degrees, we essentially cut that angle in half. And as a result, if this building was tilted towards us at 45 degrees and only appeared half as large as the building that was straight up and down, it would vanish or become unresolvable due to the Rayleigh criteria a lot closer. You see how that would work out? Because it's essentially smaller than the full-size building because it's tilted. Now, why is that important? How about instead of being tilted, the building is still straight up and down, but instead of having our eye here, looking at this angle, how about instead our eye was up here? And we were instead looking at this angle. Do you see how this is the same thing as tilting the building towards this eye? By going up, we are viewing the building on a tilt. If we wanted to see the building straight, it would have to go that way. See how that works? So, if you gain elevation on a flat plane, you actually can't see objects as far as you could had you stayed on the ground, which is the exact opposite of what we see in the real world. The reason that works that way in the real world is that we have a curved surface of the earth. We have a building out here and an observation post here. Our line of sight goes this way. However, if we look down, we can see this portion of the building above the horizon. This is hidden down here. However, if we go up to here, our horizon is actually there, even though that's level. We can see the entire building because we are getting up over the curve of the earth. This is the situation we see in the real world. Now, the last thing that I want to review is the suggestion that the Rayleigh Criterion somehow has something to do with whether or not objects are visible in the distance. Now we did one earlier on and said that 12 feet should be seen at 18 miles based on the Rayleigh Criterion. Yet according to the Earth curve calculator, it's only seen at 8 miles. This is easy to confirm. Present a photograph of a 12-foot tall object 15 miles away, sea level to sea level. Then we've got something to talk about. However, if they consistently disappear at 8 miles, that's strong evidence in favor of a curved Earth. Now, I also did another calculation on a 100-meter tall building. Based on the Rayleigh Criterion, in order to have that building disappear due to the decreasing angle, it would have to be 818 kilometers away. Yet, the building 100 meters tall disappears at 40 kilometers. Now, Flat Earth likes to talk about the Rayleigh Criterion. They like to talk about atmospheric effects, including imaginary ones like lensing and such. If they can demonstrate how an object 100 meters tall, which should be seen based on the Rayleigh Criterion out to 818 kilometers, disappears at 40 kilometers due to atmospheric effects, they need to actually demonstrate equations and measurements to show that the atmosphere will restrict your vision by 95%. If not, they are simply grasping at straws. Folks, this is Bob the Science Guy. Thank you for stopping by. I hope that this helped you a little bit and maybe did some visual explanations of things you may have been struggling with. We'll talk again soon, and in the meantime, please like and subscribe to my channel. Take care, guys.
This rabbit hole's too deep for me. Feel my brain getting real sore.